All right. Hi everyone. I'm Claudia. I'm a member of SEDS at the University of Puerto Rico at Mayagüez, and I'm also team lead for our S.U.I.T.S team. Once again, a quick reminder: this is being recorded, so please keep yourself muted during the presentation. So tonight's Space Talk is actually part of Team Prodigy's outreach for the NASA S.U.I.T.S 2021 challenge, and I wanted to take a few minutes before our speaker to talk a little bit about S.U.I.T.S. So S.U.I.T.S is one of NASA's Artemis student challenges. Students are asked to create an information display within augmented reality for astronauts. This means that students are designing an interface that will help astronauts during the Artemis mission where they land on the south pole of the moon. This includes having constant display of crew vitals, navigation guidance, tools to ease sample collecting, and others. So back in October, our team here at UPRM submitted a 40-page proposal of this for the NASA Suits Challenge, and we got selected to move on to phase two, which is super exciting because this is the first year our institution is participating in Suits. Our team is currently building a prototype of our AR concept, which is called Archer. One of the main features of Archer is actually using point-based navigation system from your current position to a 3D object position, which is what you can see on the picture on the top left. And this is a team project, so if you would like to know a little more about Suits or about Team Prodigy, you can follow us on social media. I'm going to be leaving a link in the chat. We've recently uploaded our team introduction video, which is, you can see the thumbnail here on the bottom right. And you can meet the team and see a little more of Archer in action. So we're very excited about that. I'm going to stop presenting and give it away to our speaker tonight is Mr. George Salazar. Salazar is a registered professional engineer in the state of Texas and has over 30 years of experience in the field. So we're very excited to have him tonight for our Space Talk. And Salazar, you can go ahead and begin your presentation.
All right, thank you. And I think I need to get the control for sharing my content. I don't have that ability right now. If you can give me that, I appreciate it.
It should be good. Try again.
All right. So let's see here. Okay, can you see that?
We can see it.
All right. Hopefully that's the presentation chart of understanding human interface design for space missions. Thank you for inviting me to be a speaker. My intent here is kind of give you an overall. I have to say that human-computer interface could probably take days to explain. But what I want to do here is provide a kind of a high-level definition of understanding what the human interface design for space missions is concerned. The key takeaway here is to make sure you guys understand that a human interface is not trivial. I know that obviously, as a student, you look at a human interface and say, well, I can just do this, and this, but there's other things to consider, especially if you're dealing with a space environment. So can you see the agenda?
Yes, I can see it.
Okay, so the agenda is I'm going to talk about the human and machine limitations. The human is not obviously the same as a machine, and so we have to understand first and foremost what are the limitations of the human, and what are the limitations of the machine. Understanding that, you can design systems that are suitable for the particular application. Without having that basic knowledge, it makes it a little bit more difficult and a little bit more challenging. And that's why we've had many accidents over the years, whether it's aviation, whether it's in the marine area, or in plants. It has to do with not understanding the difference or the limitations of the human and machine. And then I'm going to talk about the elements of the human-machine interface, kind of at a high level, in terms of what's involved with a human-machine interface. Then I'm going to talk about design for safety-critical applications. Again, this is more focused toward NASA applications, but obviously you can relax some of the information and use it for non-critical applications, but I'm doing it more so for NASA. Situational awareness. This is something that it bugs me that even NASA folks don't understand. So I'm going to be talking about situational awareness, and it's just not being able to see what's going on. It goes way beyond what's going on in your environment. So by the time hopefully by the time I get through with situational awareness, you'll understand what that is, and then just a few words in conclusion. So let's talk about human-machine capabilities. So this is NASA's findings on human-machine in executing commands. There's some of these that are have an asterisk on them, and basically this asterisk means that artificial intelligence is getting close to doing this capability. So from the human standpoint, hopefully, let's see if I can bring up a laser pointer. Can you see that? All right. Humans, originality and creativity. There's no question that we're very creative, and we can come up with a solution that sometimes is not in the book. We can figure out a way to solve a problem without ever been training, just what we have. I don't know if you guys are familiar with the term MacGyver. So this is an old show from many, many years ago, but MacGyver, always had a way of solving a problem by using, bobby pins and rubber bands and a piece of rock and all kinds of things that he could find to come up with a solution. And we're very good at that. The next one is rapid retraining. We can retrain very quickly. We do that quite often. In other words, we've been trained to ride a bike, but all of a sudden, we say, okay, you need to ride a scooter. Well, we can do that very quickly. Functions under overload conditions. So basically, this means that some functions are require a lot of human intervention. And sometimes we can compensate for that. Even though there's a lot of things going on, we can figure out a way to make it work as far as the load capability of performing a function. Reason inductively, from specific to broad of suitable operations. So in other words, we can take a specific option and branch out to different options that can solve the problem. We're very good at going from what we call a divergent capability, going from one option to many different options. Evaluate risk under expected events. So sometimes we look at risk in terms of what's going on around us, and we can figure out how we're going to deal with the risk, whether it's because we lost an engine, or we lost oxygen, or whatever. But we can evaluate that. Use equipment beyond its specific limits. We can always figure out ways to make the equipment work beyond our capabilities. I'm reminded of my bicycle that I had many years ago, and so I I used to try to pop wheelies, and I don't know if you're familiar with the term popping wheelies, but you can make your bike go up with just on one wheel. So if I added more air to the tire beyond its capability in the rear tire, I could pop wheelies a lot better. So yeah, use equipment beyond specific capabilities. And then certain stimuli that machines cannot. We can sense things that machines don't. Machines might be able to, sense oxygen and chemicals and stuff like that, but we can sense things like, for example, there's a rodent or a rat or something approaching us or things of that sort that the machine might not be able to. The machines, on the other hand, are very precise in repetitive motions, and that's one of the reasons why they use our machine, like for example, robots in automation, building machine cars, for example. Quicker response to time stimuli. A machine can respond much quicker than a human. That's one of the reasons why the in the Apollo program, von Braun said, when we go and launch the computers are going to basically operate the rocket. Humans cannot respond quickly, so it's the computer that will basically control the rocket and not the human. And he understood that completely because the machines can operate in milliseconds, microseconds, nanoseconds, and humans operate for the most part in milliseconds, seconds, and minutes, and things of that sort. Store and recall large amounts of data. Machines obviously can store a lot of data compared to humans. We're lucky to remember 7 things in one instance. Reason deductively, they do kind of things in the opposite of what humans do. We can do things. Machines can do opposite of humans. So they can take a lot of information and figure out what's the best solution. Functions in wider range of stress conditions. Basically, this means that the computer can operate in environments that are way beyond humans. Hot conditions, rain, snow, and things of that sort. You got computers. Obviously, they're stronger. The computer that we have, it's called Robonaut 2. It can hold 20 pounds straight out with its arm extended for an indefinite period of time, as opposed to a human can hold 20 pounds. They're lucky to hold it for a few minutes, at least some that I know. And then sense certain stimuli that humans cannot. For example, radiation. We can't sense radiation, but machines can. So these are kind of the limitations of the human and limitations of the machine. So let's look at the elements of a human-machine interface in terms of purpose. So it serves as an interface between the machine and the user to accomplish a goal through the balancing of the limitations and capabilities of the human and the machine. What does that mean? It means that if you're looking at this diagram, you're looking at the user and you're looking at the machine application at the far end. So here's the user, here's the machine application, here's the machine interface. So this machine is basically sometimes it's called the workstation. Sometimes it's called the terminal that permits the user to talk to the machine. The machine, in turn, is sending information back to the user to help the user control the machine. All right. So if we break it down, the user interface is display presentation. What is the machine presenting to me that I need to understand? Control interface. What do I need in terms of control to the machine application to control the application, whether it's robot or whatever? The dialogue. This is important. This is in terms more so in software. How do I communicate with the machine in terms of what's going on and how do I respond? On the machine side, you got the machine interface, which sometimes could be just for sake of argument, it could be just a communication cable as communication data between the machine application and the computer, which is the human-machine interface. And basically, this encompasses the application interface. So you got these elements that basically comprise the human-machine interface: the user, human-machine application, or rather the machine application, and the human-machine interface that actually translates user interface commands to the machine. The machine responds by providing feedback to the user. So making the function of the technology obvious to the user is very critical. If you're not doing that, you're basically uh, welcoming a opportunity for the user to create a mistake. If the machine is not providing status to the user in a fashion that the user can use that information to control the machine, be it a robot or a spacecraft or whatever, the it's the user is not going to know what commands to send to the machine. So if the machine is in, let's say, the machine has different states, state 8, B, and C, and the user does not know what state the machine is in, it's going to be hard for the user to control the machine simply because he or she does not know the state of the machine. And I can tell you from experience as well as history that state machines have been a big issue in human-machine interface. In other words, the human does not know what the machine is doing, what in what state. So the user thinks, let's say for example, flying a airplane. So the human might think that the aircraft is in the flight mode, but the flight computers on the airplane think they're getting ready to land, and they're not ready to land. So you got a misinformation between the machine as well as the user. And then tasks performed within small effort while improving productivity. What does this mean? This means that you're trying to minimize the amount of things that have to be done in order to improve the productivity of the system. That's something that maybe I'll say something later about. It has to do with workload as well as usability. And the bottom line, sometimes the human machine interface, and I'll probably say this many times over, is that it's the usability that tells you how receptive the user is to this system that's talking to the machine. So if it's hard for the user to understand how to operate this machine, he or she will evaluate the machine as saying, this thing is a piece of junk. I don't understand how to use it. I don't understand how it's operating. Bring me something else. So the usability starts in testing, and I'll mention more about that later, becomes very critical in terms of understanding how well the user is using the system, and more so how receptive, or how what's the word I want to use here? How willing is this user to say, "I like this interface"? So this here's a what's called a Venn diagram of basically the machine design, task design, and the human element involved. So there's a few things involved here in terms of what's going on. So in the machine design, with the task, you're trying to max the machine to the task, and I'll probably say more about this later. But if the robot requires, let's say, quick response to inputs from the user, and you're trying to use let's say, for example, a touch screen, and the touch screen says, oh, first of all, what area do you want to select? Well, I want to use user robot control. Okay, touch the user robot control. And then what do you want to use in user robot control? Well, I want to use grappler. Okay, so I'll touch grappler. And then what do you want to use? I want to close the grappler on this object or whatever. So it's taking a lot of steps to do that, as opposed to maybe just one switch function that does it all automatically. So that's what I mean about matching the task to the machine design, and then the machine to the human, matching the machine to the human. If the interface is very complicated, let's say for example it's got a 55 switches. It's going to be difficult for the user to remember what switch to use when. All right, so you have to think about matching the machine to the human. Then you have the human to the task. Match the task to the human. Is this task the right task for the human, or should we allocate this to the machine? If it requires maybe 125 actions or activations or controls to control some specific function, maybe the human is not the right person to do that because the human can't respond quickly. Maybe the computer should do that. That's something that's used very often in NASA, related to what we call safe mode of a satellite. So when a satellite something's gone wrong on the satellite, the autonomy, which basically is software, looks at all the different parameters and decides to put this machine into a state, which they call the safe state, meaning that it's conserving power, it's staying stationary, and it's not moving until it gets commands from the ground. So matching task to the human is also important. If you get all these together, you've optimized the human-machine interface, which is the intersection of all these. All right, so potential human interface design problems. Complexity and difficult to use, as I've mentioned time and time before, is that if your machine is very complicated, you're talking about potentially having a problem in terms of errors occurring. Heavy memory workload. Humans only have a certain amount of memory, and so if this machine requires a lot of command and control to operate it, it may be well beyond the capabilities of the human, and so potential for human error or problems of that sort. Inconsistency of the interfaces, particularly with different spacecrafts. This statement has to do with if you got different spacecrafts. Uh, let's say, for example, the Orion spacecraft, and then a Habitat or a EVA, extra vehicle activity spacesuit. But if the controls are different in each one of these, well, guess what? The astronaut has to think about they have to change their mode of thinking on how they're going to operate this system. So it could be they get confused very quickly. Feedback ambiguity. Oh, that's a biggie. So if your system is not providing feedback to the user about where this system is at in terms of state, operation, and things of that sort, the astronaut or the user may not know what to do next. Just think about, I guess one of the things that comes to mind is some of the early Microsoft Windows applications. I would say, like, for example, execute a program, and there was nothing on the screen to tell me, where am I? What's going on? Am I finished? Is it done? Is my system locked up? I don't know. And so the feedback is very important to understand for the user standpoint of what's going on. And if the user does not know what's going on, there's a high likelihood they're going to hit the wrong button and cause a human error. Labeling in terms of how you're labeling your system, and I'm talking about a physical system. And so sometimes labeling has to do with how you lay out your human interface. I know in some spacecrafts, the labeling says this is all power systems control. This is all environmental life support systems control. This is all related to, let's say, thermal control. So the labeling is very important. If you start mixing things like, for example, environmental life support systems with thermal control, uh, there's a likelihood people are going to get confused and they may punch the wrong switch. Critical error prevention. This I'll say something later about this, but this is basically dealing with critical commanding. And you know, the simple explanation of this one is the way you can avoid critical errors is by doing a ready, arm, and fire. So you've ready the system, and you get a status feedback. System ready. Arm the system. System armed. Fire. System firing. Okay. So you got three things that can happen. You cannot inadvertently initiate a inadvertent command by one, you know, pressing one button. You don't want to get into the situation where you press one button and you've activated a thruster or you've disabled some function that is very critical for the application. So you always got to be thinking about how do we prevent a inadvertent activation. And I'll say something later about that. And then the environment. You know, you got to think about the environment, the layout. How's it laid out? You know, for you. You know, is it very close confinement? Is it very difficult to move around? The temperature, is it very hot? You know, you'd be surprised how humans behave when it starts getting hot. You know, you start getting um, what's the word? Uncomfortable, and you start, you know, it's very difficult to concentrate on the application because you're saying, man, it's hot in here, I don't feel good, you know, I'm starting to sweat's coming down my eyes, I can't see very well, you know, et cetera, et cetera, et cetera. Contamination, you know, what kind of contamination is going on in the system? Induced effects, like for example, vibration, you know, things are starting to vibrate. How are you going to control that system if things start to shake? How are you going to control that system if all of a sudden that system is starting to misbehave because of electromagnetic interference or radiation effects as well? So human error at the bottom, and you know, sometimes I tend to say this, not human error, but design deficiencies is equal to interface deficiencies causing a mismatch between the demands of the task and the human capabilities. So in other words, you did not design the human interface to consider the human capabilities for the task that the human has to design for. And so, in a physical sense, designing the human machine interface, you got to think about the environment. Again, temperature, you know, is the system going to be designed for the temperature that's going to operate in, the vibration that's going to be operating at, electromagnetic compatibility, humidity, shock, radiation. These are the environments that can affect the hardware. If the hardware is not working properly, guess what? Your system is not operating properly, and even though the human is pressing the right button, it may not respond as it should because the system is misbehaving because it's caused hiccups, if you will. Let's say, for example, radiation. You're upsetting the memory, and you're doing bit flips on the memory, and so the application or the memory contents have been altered, and so you're changing the characteristics of the rather the behavior of the software. And in terms of the human machine interface, do you have a display that provides the right vision for the user in terms of distance? How big is this display? You know, if the user is 30 feet away, he or she may not be able to see the font size. The colors, you know, the color scheme correct. You don't want to put too many colors in there because they're going to get confused as heck as to what's going on. The glare, is there glare because of the the illumination that's affecting the system, and that's part of the environment. Hearing, okay, noise frequencies. If you're trying to provide feedback auditorily, let's say through a speaker, but the environment is very noisy, it's going to affect their hearing. If it's touch, tactile, electromechanical touch and feedback. So in touch, electromechanical switches basically are very popular, if you will, in the space environment because it's very tactile friendly. You can actually feel that switch being pushed up or being pushed down, as opposed to touch. Touch, you just hit a piece of screen. Uh, let's call it a piece of glass, but there's no tactile feedback per se. So you got to provide that through software. And in touchscreen applications, sometimes that happens through maybe a auditorial feedback as well as a rather a visual feedback, like for example a bloom, something that shows up when you touch the screen. It blooms up like a big bright spot on the screen saying, hey, I saw you, that you touched this. And so that's important, and that goes back to feedback, indicating to the user, yeah, you touched this command, I acknowledge it, I'm going to execute it. This is just I'm just going to go through this very quickly because this is part of NASA, what we call the NPR 87005, which is human rated requirements. And I just want to point out that in human rated requirements, we have specific requirements associated with human interfaces. Like, for example, in this first button, the capabilities necessary to execute the mission. So that's basically some kind of tactile or some means of executing the mission. Capability prevent a catastrophic event. So you don't want to enable some kind of event that could cause a catastrophic event. So that's where the armed fire situation occurs. The capability to prevent an abort. Well, this is the case of you're going uphill, and I say uphill, you're launching the vehicle, and so you're trying to if something happens to the system, you don't want to prevent an abort unless you find out specifically that you have to enable a particular function to abort the mission. The next bullet is just basically to tolerate inadvertent operator actions. So you don't want buttons that are open that basically somebody can bump and activate a command. Well, you didn't want that to command. That's why we have something called switch guards in place. The third bullet, tolerate operator actions. So the operator forgets from 1 month to the next how to operate the system, and the system has a way of saying, you got to operate this function before you can operate this function. So it's a way of preventing to tolerate the operator forgetting how to operate the system. This last one here has to do with more so manually controlling the flight path. And this is something like, for example, SpaceX, Space Shuttle had this, that the astronauts could take control of the vehicle and manual piloting the vehicle back to Earth. And this has happened a few times, especially during the early days of the Mercury program, Gemini program. I think there was one shuttle where they had to do that, but for the most part, it's the ability to take control of the system, get away from the autonomous system, and operate the system manually. So the human-centered design process, and I'm just going to go briefly to this, is it's basically the design process of designing something that's meant for the human. So the first thing you got to do in looking at this is to ensure the needs of the user are met. You're developing mission and scenarios. How's this system going to operate? What's the concept of operations? Okay, so these are the concept of operations. So these are the requirements. Okay, so here are the requirements. Who's going to do what? So here's the requirement allocated to the hardware, like for example, a switch. Here's the requirements allocated to the software, for example, autonomous operation. And then here's the operation, here's the functions allocated to the human. And so, you allocating the functions between the user and the system. And then you perform task analysis. I'll say more about that later in my presentation. And then visual design comes in. This is where you're developing design solutions. And then over here is to evaluate the designs to see if they're meeting the requirements. If not, you're going back. And that's what this error means. You're iterating over and over again. That's the thing about human systems design, is that there's a lot of iterations involved. It goes more beyond designing hardware and software. All right, so design considerations for space applications. Visually seeing the displays, as I mentioned, color, font, brightness, caution and warning messages. Auditory, caution and warning messages. The intensity based on where you're at. If you're in an environment that has loud noise, you got to consider that. Reverb and echo effects. If you're doing speech recognition, obviously that's a design consideration. Tactile feedback is critical. Did I really press this button? Did I really touch the screen properly? Electromechanical switches versus touch for safety considerations. Hardware switches for time critical functions. One of the things about hardware switches, they're basically you press that switch and it's going to do exactly what that switch is supposed to do. Sometimes soft touchscreen technology requires navigating through different displays before you get to the actual ending. So that could take time. You got to be guarded. You got to be cautious about that. Switch guards to protect inadvertent activation of a switch, and then switching transition to another stage, inducing a failure, meaning that that you're making sure that you have not designed the system to go into some kind of nebulous state as you're transitioning from one switch contact to another. So think about a switch contact that goes from, let's say, for example, on and off. In between, it's a nebulous state, right? You don't know what's going on. So you have to design the system to make sure it handles that nebulous state as it's transitioning. That's what that means. Command activation, must work functions. So there's functions that must work. And so you design your system to say, by golly, when I depress this switch, it's going to work. And how do I know that? I get feedback. Function grouping, this basically goes back to what I mentioned. You put all your power system functions together, all your avionics, environmental life support systems together, solar power systems together. So every function has all the switches or controls grouped together, so that way there's no misunderstanding between switching between different activation modes, if you will. Status lights. Okay, I've seen this happens many times before. The status of the switch or the system. Sometimes people say, "Well, I'm going to design the system that the switch, when I flip the switch, it's going to say it's on." But that switch was intended for a particular system function. So what's my feedback between the system function? I'm not interested whether my switch is on or off. I'm interested if my system received that command, and how do I know that that command was received? It's a big difference between knowing that the light is on and the switch is on or off, or whether the system acknowledged that switch commanding. All right, so here's an example. I'm just giving one because I know you guys are involved with speech recognition of that there are factors to consider, for success. And this is what they call a wishbone diagram, where there's a system failure, but there's different pieces that can actually affect this. You got complexity of the word load associated with a task. You got redundancy of the. So in other words, what I'm saying here is that you got not only speech recognition, but maybe you got switch functions that take over speech recognition in the event the speech recognition is really bad that day. The user is not themselves, and so they got to find another way of controlling the system, and not by voice. Recognition, adaptation. The user's voice is going to change from day to day, because of maybe they're not feeling well, or they haven't had enough sleep, or they're depressed, and things of that sort. So your system has to adapt to that. Noise and reverb, as we mentioned, is part of the environment. You got to consider that. Psychological effects, they could have a cold, and so that changes their speech recognition. In the microgravity environment, there's no sinus drain, so they sound very stuffy. So what you train on the ground is the voice on the ground is not the same in space, because they sound stuffy. Psychological, they're not feeling well. Time of day. At the end of the day, they're tired, and so they don't feel like speaking much. But guess, they say, I got to perform this task, and I got to speak to it, because that's the only way I can control it. And then speech variations. People are not consistent speakers. Morning to the afternoon. There are a lot of things affect the way how people speak. The frequency of training. How often did you train the users for this system? If you only trained them one time, don't expect the system to work perfectly the first time they use it. 6 months down the radiation effects. This actually affects the hardware. If radiation affects the hardware, you have to make sure that you have a way of designing your system to mitigate the effects of radiation. Navigation design. This has to do with dialogue. So dialogue has to do with how do you interact with the system. I keep hearing what do they call it? Natural conversation. And they talk about the Amazon. Uh, uh, I think it's I forget the name of the application. Siri, I know they use it on iPhone, so they call it natural conversation. But there's no such thing right now as natural conversation. Um, I know that I've used Siri on my iPhone, and Siri says, "How can I help you?" And I said, "Can you uh, can you compete to the 57th digit, the value of pi?" And it comes back saying, "What?" It doesn't understand what I'm saying. That's because it was not programmed for accepting that. Natural language processing, we are way away from doing that. So we got to be cautious about that. Navigation design. Navigation design, the way we can do it right now to make sure the application is suitable for the task is that you design the dialogue to direct the user into accomplishing the task. That's the bottom line. You're trying to direct the user to accomplish the task in the application. Feedback, obviously critical. Speech recognition. You don't want to say something and there's nothing coming back, and the person goes, did it recognize me? Is it stuck? What's going on? I don't know what's going on. I'm not getting no feedback from the system. So you got to provide feedback. Error correction. Sometimes error correction is important to correct speech recognition errors. That does take up some time, so you got to be cautious about it. Confusability. I think I talked to some of the folks earlier about confusability matrix, basically saying which words are confusable in the application. You got command words that could be confused. The confusability of the words and confusability matrix basically identifies which words are problem words, and you have an opportunity to change those words to something else. So let's talk about errors and failures where they can occur. And so from a hardware standpoint, and so let me just point out that these are the four elements, key elements of system design. You got the environment that the human's involved with, you got the environment that the hardware is involved with, and you got the software as well. This is what we call the human systems integration system view. In other words, the human element is part of the system, but that human is in the environment as part of the hardware and software. So from the hardware standpoint, the errors can occur because hardware tends to fail over time. Physically, it starts to degrade, it starts to get bad, And so, like, this is called the bathtub curve. So early on, the burn-in phase, there's a high failure rate, but once you burn in hardware, you have a constant failure rate, and there's a computation that you can do, whether it's mechanical or electrical, using the exponential function, e to the minus t over mean time between failure. And so you can find out with what's the likelihood of a system failing over a period of time. But after a certain point, there's a wear out phase that happens just simply because things are getting old. Mechanical systems start to fail, electronics start to fail because being turned on and off over a period of time because they've been exposed to total dose radiation over many years. And so you got to factor that in. Now, software is a beast. It's a totally different beast altogether. Unlike hardware, software doesn't have components that fail. What does fail is writing the software code. So initially, you write software code, and you have a failure, but you start identifying what those software errors are, and you basically wring them out of the system, and you minimize them. And everything is fine until you upgrade the software to another point, and then you start all over again. And then you upgrade the system, the software again, and then you start all over again, trying to get rid of the bugs, et cetera, until you stop upgrading the software, and then now you have a constant failure rate. So software failure rates and hardware failure rates are much different. Failure rates of the human, oh my gosh, that's a really complex problem. But there's so many failure rates of the human that can occur, both due to physiological and psychological factors. And then there's the human-machine analysis process that deals with trying to mature the technology. So you develop first the concept of operations. From the concept of operations, you develop requirements. From the requirements, you're allocating requirements, like I said, either to hardware, software, or the human. And you do a task analysis. Based on the requirements, you develop a list of tasks. And you look at the human errors associated with that. I give you an example here that there's different error types, and it depends on the application. But I'm saying here, error type 2 is an action omitted. An action has been omitted. And what's a recovery? Some alarm is announced that the astronaut identifies and basically corrects the omission of an action. And the consequences is, let's say, for example, the action has to do with pressure, that the pressure is increased, which causes an alarm to alert the operator. So that's part of the task analysis, human error analysis. Going back to the requirements allocation, you're designing a system, you're designing a prototype, you're doing human in the loop testing, seeing how well this system is operating based on the requirements. And then you perform usability studies and workload, and then situational awareness. I'll mention more about that later. And then you go back to human error analysis. So there's a lot of activity going on here as well as here. And so it's not a trivial thing to do. Human error classification, you got two kinds here. I'm just going to briefly go over these. Skill-based errors related to slips, which could be a failure of attention of an action that's carried out that is not intended or planned. And then lapse, lapse is a memory failure. You just simply forgot. And then there's mistakes. Mistakes is rule-based, which means that the user used the wrong rule for the situation, or knowledge base, which means the mistakes resulted from insufficient or incorrect information. Knowledge base happens very commonly when you're developing new technology. And then violations basically is meaning that you intentionally did something to sabotage the system. And for the most part, we can neglect this unless you're a terrorist. We'll assume everybody's not a terrorist, so you can avoid this. But this is part of human error classification. And then situational awareness. So situational awareness is to identify, process, and comprehend information about how to react to a situation. So the first thing is perception, aware what is going on and happening in the process. You got the environment dynamics, the current state of the environment. Here's the perception of what's going on. And then there's the comprehension, understanding the state as it is now when the perception occurs. So this is a comprehension. And during the comprehension, you got an interface design and workload. So you're looking at feedback from the system and all the data that's coming back, and you're trying to comprehend that. That's part of the comprehension. And your action, understanding what is to be done in the future. Your reaction is your decisions based on all this data that's coming in, what you perceived, what you comprehend, and then your action is taken based on your mental models. Your mental models is basically how you think the system is supposed to be operating. And then you look at the results. Did it accomplish the goal? And then you go back to the current state of the environment. Did I correct something that went bad? That's part of situational awareness. Did I correct something that went bad? And that's what this is all trying to convey to you. You got to keep in mind that humans have one pair of eyes and hands, one mouth, and limited attention and cognitive resources. So you got to keep that in mind as you're developing the system. Situational awareness drives decision and performance. You know, if your situational awareness of the system is not very good, your decisions, your actions, and the results and your goal are going to be much different than what you expect. And contributing factors to the loss of situational awareness can be spatial disorientation. Is it this way? Is it that way? Am I looking at 3D, two-dimensional, three-dimensional? System awareness, system status, confusing, a new environment. That cartoon says, if you can't read, it says the field light is on, Frank. We're all going to die. We're all going to die. Oh, wait. Oh, my mistake. That's the intercom light. So depending on how it's laid out, you can get into a situation that it should not have been a bad situation, but the way things were designed caused that to occur. Task awareness, you're competing with tasks. Are they difficult? Demands of each task could arrive in or leave. You know, so sometimes they say, oh, we'll do test 1, test 2, test 3. In reality, you're doing test 1, 3, 1, 2, 1, 3, 1, 2, 2, 3, 2, 1, 2, 1, 3, 2, 3, 1. They're interleaved. It's not sequential where you can predict how you're going to operate the system. You got to be prepared for that. Task awareness is very critical, as well as system awareness of the system. And then maturing the human machine interface. So in the middle, there are key elements that are going on in maturing the technology. The workload. How much work is this taking? This is something called the workload analysis. And then, which basically says, was it possible to complete the task? No, then forget it. Let's doing something else. Was the workload tolerable for the task? Yes. Then you continue, was the workload satisfactory without reduction? Yes. If not, these are the look at the insufficiencies or deficiency of the system. And this is part of verification, because you're trying to verify your system that it meets certain workload requirements. And then usability. This is very important. Is this thing usable? And usability has to do with effectiveness. In other words, how much errors am I introducing to the system using the system? How many steps for success? Efficiency, step task completion time. How long does it take for me to do this? Deviations from best path. What are my deviations in order to come up with the best way? Satisfaction. This is clearly an important one. System usability scale. There's a usability scale to figure out how satisfied are you using the system. In the background is situational awareness in all this. And then situational autonomy is, there's different levels of autonomy. You got level 1, which has to do with, like, for example, telerobotics operation. You got level 2, which is automatic operation, like, for example, sequencing a power up distribution event. Okay, it all goes through an automatic sequence. But then you got level 3, which is semi-autonomous operation. An example here would be, let's say, for example, an automobile that's in cruise control, but you are also have awareness of what the computer, or rather what the car is doing. So the autonomous portion is cruise control, but you have the ability to take over the cruise control in the event that you get ready to crash, right? And then the last one is full autonomous operation, where the car, let's say, and an example is the car is doing everything for you. You relax and sit back and let the car do all the riding for you, all the driving for you. But you got to be cautious. Automatic only when necessary. Automate only when necessary. Keep the operator in control and in the loop. In full autonomous operation, as what happened tragically in Florida, that the person died in that Tesla car that had autonomous operation, and the car did not recognize the truck in front of it, and they collided with it and killed the driver. And then make mode and system states salient. In other words, the user should always know the state of the system at all times, at all tasks, and all operations. If not, it's very easy to get out of sync between the user and the system if he or she does not know where they're at. So these were just examples that I wanted to show. Chandra X-ray Observatory had a fully autonomous mode. The Chandra went into a state where it lost a thruster, actually a reaction control wheel for gyros for understanding where it's located. And so it went into a safe state. It started to shut down a lot of things, and then it started to send automatically a signal back to Earth saying, "Hey guys, I'm in trouble here, help me." So this is just something to be aware of if you're involved with autonomous systems. And so, in conclusion, understanding HCI for space application requires many aspects of it. You have to understand the environment in terms of the hardware and the human in that environment, the software in the human-machine dialogue, and the hardware as far as the human and input-output selection as well. So all these elements are part of the human-computer interface. It's not just punching buttons and seeing the display. As you can see, there's a lot involved here. So with that, I think that concludes my presentation. And let's see if I can return control to you guys. Okay, so I think I returned control. I'm sorry I went a little bit over, but I can certainly try to answer a few questions.
That's okay. If anyone has any question, feel free to write it in the chat or unmute yourself and ask. Salazar, I have a few questions from people who signed the registration form. Sorry. So someone asked, do you have any book recommendations on human interaction design of space vehicles?
Recommendations for human interaction with space vehicles?
Yes.
Wow, that's a big one. So the thing is, it depends on the space vehicle, but obviously the human interaction is not just the human sending commands to the vehicle, but it's also the vehicle providing appropriate status back to the human. And so when you're designing a system that controls a robot, a car, or whatever, you have to make sure that you understand what each command does to the system and what you expect from that system to let you know that things are going correctly or incorrectly. Otherwise, you guys are going off in different directions. You think everything is hunky-dory, but the system says, "Hey, I'm in trouble here," and the user thinks, "No, everything is fine because I'm not getting no feedback from the system." So it's not a it's not a trivial thing, and that's why you know there's people can get master's degrees and PhDs in human computer interface, and because it's a big subject, a lot of challenges. I know I'm involved with many different organizations associated with human computer interface, and the military is struggling with this. Federal Aviation Administration is struggling with. NASA struggles with this. In fact, human computer interface is one of the 33 risks associated with a human research program. Just simply because the future systems for deep space applications, where going to the moon and Mars and beyond, are going to be very complicated. So we have to come up with better schemes of human-computer interface. It's not trivial. It's there's a lot involved. So you got to think about the hardware. First of all, the hardware has to be meet the environment, right? Second thing is the software has to be safety critical, and that's part of the design of software. And then now you do the interaction, making sure the interaction is correct. Am I getting the right feedback from the system, and am I sending commands properly to the system based on the feedback? And then this goes into situational awareness. Okay, so based on what I'm perceiving right now, I'm comprehending that the system needs this command, or I'm comprehending that I don't need to do anything, and so my future actions require this, and this. And so if you don't have that situational awareness of the system and the user, again, the system can go south on you, and you can run into problems. Like for example, the USS McCain. They had a touch screen on there. I think it was about 2 years ago, and so there was a lack of feedback between the user and the system. And make a long story short, the user did not know what was going on, and they were on a collision course, and they did not know that. It was too late. They collided with another ship, Navy ship, and 5 people died. So feedback is important, critically important. Situational awareness is important too as well. Unfortunately, you guys are not taught this in school. That's the unfortunate part, and it's just not in Puerto Rico. It's in the United States as well, and that's been my mission, is to try to convey this to students to understand the human element. I did electrical engineering from undergrad, master's of systems engineering from a grad, but I can tell you, virtually nothing was related to the human element.
Awesome, thank you. So one last question before we close everything up. Everett from Napa Valley College asked, what are three key design considerations for interfaces when dealing with an environment like space?
I'm sorry, can you repeat that?
Yeah. What are three key design considerations for interfaces when dealing with an environment like space?
Well, the big issue with space is, especially we go beyond the Earth orbit, outside of the Earth's magnetic field, is the radiation effects on electronics, and so that's something that we're struggling with. In fact, I'm involved with some research work in dealing with what we call graphics processing units that are radiation tolerant, because right now graphics processing will not work beyond Earth orbit for a long period of time. So the radiation environment is very unforgiving on hardware. And so if you look at what's going, I mean, if you don't design for the radiation environment, what's going to happen is your interface is going to misbehave. When your system starts to misbehave, you're going to get bad commanding to the vehicle. And some of that bad commanding could be not so catastrophic. Some can be catastrophic. The catastrophic stuff is bad news for the astronauts. You don't want that to you know to get to that for that to happen. So when you're designing for the human, for designing a human computer interface, again, you have to think about the environment. You got to think about the task, and at a minimum, you got to think about the task and you got to think about the environment, because the environment is going to affect your hardware, and you got to design for for that environment. And then the task, you got to think about who's going to do what, whether it's the user, the human, or is it software that's going to do that for you. And so it's not straightforward. It's not straightforward. In engineering, for those of you who are double E's, you're given these homework problems that say design an amplifier, to output a signal, from plus or minus 5 volts AC, or for mechanical engineers, design this robot arm that can handle 25 pounds of force at the edge, things of that sort. So, it's those are, I have to say, those are trivial compared to dealing with the real world, and the real world has to do with controlling systems that require human input, and that's something that's just not taught in undergraduate school.
Thank you for your answer. So it looks like we don't have any more questions in the chat, so I'm going to stop recording